Good morning, AP Physics students. This lesson covers a little bit about the lab that you guys did yesterday, or the activity. Talks about elastic and inelastic collisions some more, and introduces a new formula that you haven't seen before. We're starting things off with a collision from an AP test question. And it's a classic AP test question. It's got a paragraph and a graph that you have to deal with. And they tell you some information in the paragraph about how fast the carts are moving before and after, and then they give you a graph that shows the force over time of the collision itself. And they ask you to calculate how fast the 2 kilogram car is moving. Let me grab a highlighter here. So they ask you to figure out, calculate how fast it's moving after the collision, and then they want to know what's the mass of the second car, which I put both those answers over there so you can see if you're actually getting them right. I'll give you a hint. We're dealing with momentum still. You shouldn't be using kinetic energy or anything like that. And so what you should be doing is thinking about what this graph's area can mean and how you can use it to get your answer. Think about the force that's acting on this car, and if we have any formulas that relate that to momentum. And then you need this answer to get the next question. So if you can't figure out A, you can try B. B says calculate the mass of the second cart, and if you calculate out a collision between these two objects based on the information that they have given you here and that piece of information right there, you should be able to calculate the only unknown, which is the mass of the second car. All right, so go ahead and give those a try, and I'll go over the answers. Make sure you pause it. Okay, let's I think you hit that. Yeah, okay. So let's go over the answers. So these are kind of written out by College Board, and they don't really show their algebra too well, but we can go ahead and explain it. So area, remember I talked about the area? Area of a triangle is just going to be 0.5 times 10, and they're saying that the units were actually kilonewtons in milliseconds, which you maybe didn't even notice. They cancel each other out actually. So the area of the graph is just 1/2 times 10, or 5. And it's 5 Newton seconds of impulse. It's a force times the distance. J is the symbol for impulse. That's not joules. That area is 5 Newton seconds of impulse, which means the change in momentum is going to be 5. Now they put a negative there. Now the reason they did that, which is obviously important, is because a positive 5 would actually make our car go faster. Uh, and if you put the positive 5 in there and did the math, you might have thought that was a little odd. Like usually when you crash head on another vehicle, you don't go faster. And so this is a negative change in momentum. And so the other object got a positive change in momentum. And so with this negative change in momentum, we have to put a negative 5 there because it's a negative force. And then all this is right here is the change of momentum is, I tend to write it a little bit differently. I'll write that it's mass times velocity final minus velocity initial, but all they're doing is distributing the mass of 2 to both objects, to both variables. Nothing too crazy there. And then you just solve. You get that it's 1/2 meter per second. It's positive, so it's to the right. So we slowed down from a velocity of 2. After we collided, we only had a velocity of 1, which you will see in this next solution right here. So in order to figure out the mass of the second car, they used the information of 2 and 3, the givens, because we had a 2 kilogram object traveling with a velocity of 3. Those numbers are right there. And then after we crashed, and we slowed down. So we're still a 2 kilogram object, but we only had a velocity of 1. And so here's the formula right here that they're using. And that it's just momentum equals momentum plus momentum. And so the only unknown is actually the mass of the second car right there. And so they were able to solve that out. Okay, your lab. I'm not going to go over like all the calculations and all the numbers, but I'm going to go over what you should have seen. So the first thing is that none of these should have lost momentum. Momentum is conserved because of Newton's third law. So actually I didn't make black highlighter, all collisions, momentum is conserved. Just straight up. Momentum is conserved. You can put a dot after that. Complete sense. Momentum is conserved. It's because Newton's third law is always conserved. So every collision, inelastic, elastic, no matter what, momentum before equals momentum after, as long as the system didn't lose any mass. If you have mass leaving the system, then you got to include that mass. But if you have a closed system where no mass leaves, then the momentum before equals the momentum afterwards, or the momentum of our entire universe never changes. One object gets momentum, another object lost the exact same amount. Um, so you should have seen the momentum staying the same. Now, about energy. Not all of these lost the same amount of energy. One of them lost a lot of energy, and it should have been this one right here. And the reason it loses a lot of energy is because these objects are going opposite directions. And what they're going to do is they're going to exert a force over a distance on each other. And when they crash, when you're going opposite directions, you actually come to a complete stop. And so you should have seen that that's what happened here. Now, if they bounced off of each other, you didn't set the elasticity to 0. You gotta set the elasticity to 0. But if you did that, you'd find that these two cars actually slammed into each other and got stuck. So it would have 0 kinetic energy afterwards, and that's probably going to mean that it lost the most. Now, on to the last one. What type of collisions are car crashes? They're inelastic. And so, real world, what type of collisions? Inelastic is the answer to that question. Where does the energy go? Work. Work equals a force multiplied by a distance. And so when a car drives into another vehicle, it exerts a force over a distance as it crunches. And that makes it inelastic. So anytime you have vehicles hitting each other and crunching in any way, energy was lost. You don't bend steel for free. And the more destroyed the cars are, probably the faster they were going and the more kinetic energy they originally had. So car crashes are definitely inelastic, and the energy goes into heat, it goes into sound, and it goes into bending the heck out of the car and breaking it. Okay, there's a lot of math on the board, I know. I'll try to make sense of it, but long story short, you already have seen one formula right there. This second formula just says kinetic energy initial equals kinetic energy final. Because for an elastic collision, these are both true. That's what makes a collision that's what makes a collision elastic, is that the energy doesn't get destroyed or turned into heat. It stays in the objects, meaning you got bouncy balls, basically. Now, here's the thing. That formula is really, really, really hard to use. This one right here. Because it's got these squareds, if you do two equations, two unknowns, you can solve questions. But oftentimes it takes an entire piece of paper, and you have to do a lot of foiling and a lot of algebra too. So physicists figured out that there's a much more useful third equation down here. That equation literally says velocity 1 final. I'm going to write it with primes. Velocity 1 initial plus velocity 1 final equals velocity 2 final plus velocity 2 initial. Which you could just, basically we can just rearrange those, and I don't even need to erase that. I can just erase that, put that there. Basically, velocity 1 plus velocity 1 final equals velocity 2 plus velocity 2 final. That's really cool. Why am I allowed to use that? Well, that's what this slide is all about. So we take, and I'm going to be doing some highlighting and trying to explain. So we take the first formula here, and we're not going to use it for a little bit. We take this second formula here, and the first thing they do is that let's see if I can get a highlighter no, I'll just use pen here. And the first thing they do is they do this step right here, where they're actually just moving one thing to one side and moving it to the other side. And you can see they did that because on this line, that's where those negatives came from. By subtracting something on each side, you end up with those negative signs down there. All else they did on this little star one right here is they multiplied everything by 1/2. And then you can see the mass they just pulled out. It makes sense because you have M1. Okay, let me grab a highlighter that's like blue or something that should show up. Yeah, you have M1 here and M1 here. So they want to group the M1s together. So that's why they're pulling that over there. So you can see once they've grouped them together, it's a little bit of a dark color. I'll go a lighter one. Let's try this. That's much better. Okay, so they want to group these M1s together. So they move this over here, which is going to cause that negative sign. So you'll have a negative V1 final. See? Negative V1 final squared. And so then after they moved that over there, then they just factored an M out of both terms. They just pulled the M out. And so now you get to this line. And we're going to need that line in a second. Actually, one more line down. So then they did the difference of two squares stuff because you have, I think that's what it's called. It's been a while since Algebra 2, but that's how they did this right here. So they expanded that on both sides of the formula, doing the exact same thing. So they did that over there, and then over here they did the exact same thing. Now I boxed that because it gets used. Then what they did is they took this top formula and they brought it down here. And once again, they did a little bit of a rearranging and pulling out of mass. And so they were able to build this formula down here that I'm going to highlight orange. Now I've got some colors I can refer to. All right, so if you look at orange and you look at the blue formula and the green formula, what you'll notice is they have something in common. Purple. Well, maybe not purple. Anyhow, I guess I can go for a really light color. I don't know. I'm running out of color options here. Anyhow, if you look carefully at M1, V1, initial, V1 final, it's over here also. M1, V1 initial, V1 final. So they're actually literally just subtracting one formula from the other formula. And what's left? Well, what's left, we'll go ahead and indicate in a specific color. We'll use the, I guess we'll use the light pink. What ends up getting, that is not light pink. I guess all I have is yellow. A lot of these colors are too dark. So this is what ends up getting left over. That's pretty clear. When you take the red box and you subtract the orange formula from it, what gets left is the yellow, or this guy right here. All right, this is your new formula. There are three formulas on the board currently. There's this one you already knew, momentum initial equals momentum final. There's the new formula we haven't really used much, kinetic energy initial equals kinetic energy final. And then it's actually pretty useless. We don't use it that much because it's annoying. So instead of using that one, we use this one down here a lot. And this one that I'll color in green only works when this is true, or when you have what we call elastic collisions. So you can't use that formula all the time. You can only use it when you have elastic collisions. This is an elastic collision. We'll go over how to calculate it. Your homework assignment has one inelastic collision and two elastics. Okay. Sorry if that last minute or two just really didn't make any sense. The good news is all you really need to understand is that kinetic energy initial equals kinetic energy final, which is that 1/2 mv squared formula. And basically, if you take this and you shove it into that, you could turn it into that, which means we have a new formula that is useful for elastic collisions. So here's our elastic collision example. It has a 2 kilogram object hitting a 3 kilogram object. I believe it's 5, and I believe that's -5. I can verify that here. Yeah, -5. So, and we don't know the final velocity of either object at all, but we know their initial velocity. So that feels like a standard situation. Like I don't always know how fast things are going to be moving after they hit, But if you take a 5 and a -5 and you throw them at each other, and one has a mass of 2 and one has a mass of 3, you can solve it. Start with this formula, which doesn't get you the answer, but it gets you pretty close. We only have 2 unknowns there, and it's a nice simple formula. And then we do have to use our other formula, which is our momentum conservation. Long story short, we can take the smaller formula and we can turn it into this kind of form. So we can do a substitution. And then you can see that I am subbing in. I like the highlighter for this. What I'm doing is I like the yellow highlighter. I'm plugging in that right here. And then I have to distribute the 3, and then I end up with something that looks like this, which is actually totally solvable. It only has 1 unknown, and I can get that the velocity of the objects are -7 and 3. And I use an inelastic collision simulator to come up with this problem, and that way I can check the answer, and yep, the answer is -7 and 3. So really cool formula. But remember, the big idea from today's lesson is that elastic collisions conserve energy, inelastic collisions don't. And if you want to use your new toy over here, the powerful formula has to be elastic because it's coming from that. So you cannot use the velocity final, velocity initial, velocity final, velocity initial formula unless kinetic energy is conserved. Sorry about the lesson, a little bit longer than normal. I try to keep these as short as I can, but this is kind of a lot of math to explain. Have a great weekend, guys. There's going to be an email this weekend with some more details, and we'll just keep going as we keep going. All right, have a good weekend. See you guys Monday.